So now you know how to perform complex Morlet wavelet convolution to extract time frequency features out of EEG data that contains many trials, and you can do this over many different frequencies. The one thing about Morlet wavelets that we have been intentionally ignoring so far, is the key parameter that defines the trade-off between temporal precision and frequency precision. And this is the parameter that is commonly known as the number of cycles. So this is a term you might read in papers or hear in talks. Here we have the Matlab implementation of a complex Morlet wavelet. Here you see the complex sine part, and here you see the Gaussian. So e to the minus t squared over 2, and all of this stuff is s and then squared. In fact, this is really the parameter of 5. This division by 2 pi f, this just scales this number per frequency. So this is really, and this of course you don't really have any control over. This is the only parameter in the Morlet wavelet that you have some control over. So here it is written a different way, e to the minus t squared over 2s squared. It's a little bit clearer to see in here. And then of course we have to define s. This is also known as the width of the Gaussian, and it's some number of cycles divided by 2 pi f. Okay, so what I would like you to think about for a minute is what you would expect the Gaussian, so we're not yet going to look at the entire wavelet, just the Gaussian. What would you expect the Gaussian to look like if s were smaller, so let's say the number of cycles were 2 or 3, versus if s were larger, so the number of cycles corresponding to maybe 10 or 12 or even 15. Okay, probably you had something like this in mind. So here's almost exactly the same Gaussian in these 4 plots. It's the same sampling rate, the same time vector, the same frequency used for the scaling. All I've changed here is the number of cycles. And you can see that with 2 cycles, for example, the Gaussian is very narrow, and with 15 cycles, the Gaussian is very wide. So that's not too surprising, that kind of makes sense. Now what I would like you to think about is what the effect of this is going to be on the Morlet wavelets. So I'd like you to think about what a Morlet wavelet would look like when we use these different number of cycles in the Gaussian. Okay, I'm sure you had something like this in mind. These are not exactly the same number of cycles as in the previous slide, but that's okay. So here we have almost exactly the same Morlet wavelet, the same frequency, the same time range, the same sampling rate. Everything is the same except the number of cycles used to construct the Gaussian as part of creating this wavelet. So you can see this is not very surprising now that the number of cycles defines basically how steep or how narrow this wavelet is in the time domain. And so now, before we go on to the next slide, I want you to think about what the effect of Morlet wavelets with different number of cycles will be on the temporal precision of the results from Morlet wavelet convolution. And to think about this, now this is another situation where it's really useful to understand how convolution works in the time domain as sliding dot products, and also how time domain convolution is implemented in the frequency domain as pointwise multiplication of the Fourier spectra. And so to think about how this parameter, the number of cycles, affects the temporal precision of the results, it's useful to think about wavelet convolution in the time domain. So think about at each step in the time domain, we have the EEG data lined up here with these wavelets. And now think about computing the dot product between, let's just think about the 3-cycle versus the 7-cycle wavelet. So the 3-cycle wavelet goes to 0 much faster. So any EEG activity that's happening here is not going to influence the estimate of the frequency-specific activity assigned to this time point, which is going to be assigned to the time point corresponding to the center of the wavelet, so here. So that means the temporal precision is relatively better with 3 cycles. Now you can think about this the other way with a 7-cycle wavelet. Something that's happening out here is actually going to influence the activity or the estimate of activity happening at this center time point. So the wavelet with 7 cycles is going to have worse temporal precision because dynamics in the data that are further away from the center of the wavelet will actually bleed into or smooth into the estimate of activity at corresponding to the center of the wavelet. Okay, so this is thinking about it in the time domain and the effects on the temporal precision of the results. Now let's think about how this is going to affect the frequency precision of the results. And now what you can see here, this is a little bit confusing initially because these are Gaussians, just like what I showed 2 slides ago. But 2 slides ago I showed Gaussians in the time domain. Here what I'm actually showing is Morlet wavelets that I created in the time domain and then took the Fourier transform up. So this is the power spectrum of wavelets with a different number of cycles. And now it's quite striking and quite interesting to compare the shape of the Gaussian in the frequency domain of these different wavelets. And remember, these wavelets are all exactly the same in terms of the frequency and the sampling rate and the length of time. The only difference between these 4 wavelets is the number of cycles used to construct the Gaussian. So they all have a peak at 6.5 hertz, but the width varies quite considerably from 2 hertz up to 15 hertz. So now we can think about the effect of having a different number of cycles on the frequency precision of the results. So if you use and the best way to think about this now is convolution, time domain convolution as implemented via frequency domain multiplication. So imagine this is the power spectrum of the wavelet, and imagine you have the power spectrum of your EEG data, and you're going to pointwise multiply them, which basically means filtering the EEG data according to the frequency characteristics of the wavelet. So now you can see that the wavelet with 15 cycles is going to be fairly frequency band specific. The width here is going to be fairly narrow, just a few hertz. Whereas with this wavelet with 2 cycles, we get actually very poor frequency precision, and in fact this wavelet with 2 cycles, even though the wavelet is at 6.5 hertz, something that's happening at 13 hertz is actually going to influence your estimate of 6.5 hertz activity. So I mean, it's not going to be a huge influence, right? I mean, at 13 hertz, this is only maybe 0.2 or something like that. So it won't be a huge influence, but it will actually influence the results at 16 hertz. Okay, so now we can plot these 2 characteristics of the wavelets and the time domain and the frequency domain side by side. And again, just so you're not confused, this plot on the left shows the Gaussian in the time domain. So here time is on the x-axis. And this plot on the right shows the frequency spread. So it shows the Morlet wavelet in the frequency domain. And now you can see that with fewer cycles we get better temporal precision, but worse frequency precision. And with more cycles we have the opposite. So we have better frequency precision, but worse temporal precision. So this is the fundamental trade-off between temporal precision and frequency precision. And unfortunately, you're kind of stuck with this trade-off. So in practice, you always have to find a balance between these 2 sets. If having temporal precision is really important in your experiment, if you really want to know whether something is happening at 200 milliseconds versus 260 milliseconds, then you will want to use a wavelet with fewer cycles, and then you will just have to sacrifice the frequency precision. In contrast, if you want better frequency precision, you want to dissociate some activity that's happening at 6.5 hertz versus 7.8 hertz. Then you'll have to have a wavelet with more cycles, so 12 or 15 or maybe even 20. And of course, that gives you worse temporal precision, but sort of that's how the world works. If you really care about both the temporal precision and the frequency precision, then one option is to analyze your data twice. Once using wavelets with cycles of 3, let's say, or 4, and once using wavelet cycles of 12 up to 20 or something like that. So now from these two analyses, these will provide complementary information. You'll know from the one analysis that your dynamics are localized to such and such frequencies, and you know from the other analysis that your dynamics are localized to such and such periods of time. Okay, enough theory. Let's see how this looks applied to real data. So here we have exactly the same EEG data and almost exactly the same wavelets, so all the same frequencies and everything like that. The only thing that differed is that here I used 3-cycle wavelets and here I used 10-cycle wavelets. So here's the question. Which one of these two reveals the correct insight into what is happening in these data? Of course, the answer is that both of these analyses are equally correct. They just provide insights into different features or different aspects of the data. So we can see, there's a few striking differences that I'll point out very briefly. So here with this 3-cycle wavelet, remember now we have better temporal precision, but worse frequency precision. So it's like we're smearing the data or sort of stretching the data on the frequency axis here. So here you can see that this beta band activity is actually not really continuous, but is bursty. But here it seems to be, well, I wouldn't really call this broadband, but you don't really know exactly what frequency this is occurring in. Here we see that this theta dynamic seems to have two independent bursts, so one burst here and one burst here. And now you look over here to the 10-cycle wavelet plot, and you can see now we can localize this beta suppression much better in frequency, and we can much more clearly see that there are two completely independent frequency dynamics happening in these data, which is really difficult to interpret from this result. Okay, so here you see the trade-off in practice and real data, and probably you're thinking now, maybe you're thinking two questions. One is, do we really need to use integer cycle wavelets? The answer is absolutely not. The number of cycles can be any number you want. But in these sort of educational examples, people tend to use integers, I think just because they're lazy and I'm lazy, and it's easier to type and easier to write integer cycles. You can use any number that you want. But the more important question is, isn't there a way to find a balance between these different extremes of wavelets? And of course the answer is yes. And this is, I would say, the most typical set of parameter, or the most typical approach for parameterizing wavelets in the literature. And so here the idea is that you vary the number of cycles as a function of frequency. So at the lowest frequency you start with 3 cycles, or maybe you want to start with 4 or 4.7 cycles. And then at the highest frequency you go up to 10 cycles, or 11.98 cycles, or whatever you want. Okay, so let's switch to Matlab and take a look at some of this stuff. Let's see. So the first two cells just recreate the plots that I had in the PowerPoint side, so I won't really say much about that. All right, so now this third cell, which starts on line 44, here I'm going to create a time frequency map of the data at 01 from 2 Hertz to 40 Hertz. Using these 4 different wavelet cycles that correspond to these different parameters that I have here. In this script, we are going to be performing decibel normalization. If you already are familiar with decibel normalization, then you will be able to interpret this line. Basically, the dB is just 10 times log 10 times the power during the trial divided by the power during the baseline period, which we specify up here. If you don't really know what dB normalization means, or you're not very familiar with it, then don't worry about it. You can safely ignore these lines. You can ignore line 99. There will be a lecture about this in the future. But the main advantage of having dB normalization here is it puts all the plots in the same color scaling so we can see it. Okay, so this is fairly straightforward. Otherwise, it's all stuff you've seen before. We're looping over frequency to compute a wavelet convolution, and then we extract the power averaged over trials. And here's another loop to go over the number of cycles, which is these 4 items here. And then at the bottom, we're going to plot the results. So you can try running that line, and of course it crashes. It's crashing on line 95 because this variable AS, analytic signal, doesn't exist yet. It doesn't exist because there are 3 lines of code that are missing after the comment on line 91. Now, these 3 lines of code are also listed in the next cell down below. So if you really want to, you can just scroll down and copy and scroll up and paste. But I would encourage you not to do that, but instead to pause the video and try to create these 3 lines. And here's your hint here, as these are the 3 things you need to do on your own without looking down. Of course, the only way to learn how to program is by actually programming. So you should see this as a bit of a challenge and pause the video and try to fill in these 3 lines. All right, I'm sure no one here cheated. So anyway, let's see. We need this variable called AS. So the first step is to run the meat of convolution. And so to do that, we want to pointwise multiply the power spectrum of the complex Morlet wavelet by the power spectrum of the data. And then we want to take the inverse Fourier transform of that. So this is the first thing that we need to do. That's run convolution. The next thing we need to do is trim the edges. That means to cut off half the wavelet from the beginning and half the wavelet at the end. So let's do, I think it's called half wave or something. Yes, +1 to end minus half wave, like this. And the last thing that we need to do, because this is now, this variable is now one super trial that's concatenated from all the trials. So we want to reshape it back to be 2-dimensional, and that is time by trials. So let's reshape AS_EEG.points, that's the number of time points, and EEG.trials. All right, so now we can run that cell. And here we go. This is kind of similar to what I showed in the PowerPoint slide, but I took more extreme values here. So you can see this does not look really pretty here with 2 cycles. This is an extreme value, and unless you have a really specific need to really get high temporal precision, I would generally not recommend going down to 2 Hertz. Again, there are cases where it could be appropriate. You can see the difference between what we see in these temporal dynamics with 2 cycles versus with here at 6 cycles. So, and here 15 Hertz. Again, this is also somewhat of an extreme value, and I generally wouldn't recommend going all the way up to 15 cycles unless you have a particular good motivation. Of course, there's always going to be examples where it's the best thing to have 15 or maybe even 20 cycles. Okay, so that's interesting to look at. And now here, the next cell, I'm not going to spend too much time on this. This is basically the same thing. Mostly, I just wanted to show you the code for how it works to have a range of cycles. So we are going to have these cycles range from 4 to 10. And these are going to be logarithmically spaced according to frequency. So just so you can see this, so now this is the number of cycles. We can even plot this. Actually, let's do here plot fix and then n cycles, and let's do something that looks like this. So now you can see this is the frequency of the wavelet on the x-axis, and this is the number of wavelet cycles for each frequency. Okay, so we can run that, and now we can, let's pull out figure 3, make it a bit bigger, and now you can see this analysis with a range of cycles, I think, provides a nice balance between temporal precision and frequency precision. Still, we don't actually get out these two separate bumps here, so maybe you would want to go back and start this instead of at 4 cycles, maybe even start it at 2 cycles. Actually, let's just try that now and see what happens. Yeah, well, okay, so we still get a little bit of this, a hint of this second burst here, although this is very transient, so it's really difficult to piece out. Okay, but the important thing here is you can see the importance of parameterizing or finding an appropriate range of parameters for your wavelet analysis. And so this is really a non-trivial parameter, and you should really never do an analysis where you don't change the parameters a little bit to see what the effects are on your results and to get a better insights into what's really happening in your data. Okay, let's see. I think that was it. I hope you found that informative, and see you in the next lecture.